Welcome to learning target number 8. In this video, we will cover the learning target where you will learn to be able to describe and define the second law of thermodynamics and also the term entropy. So let's start off. What is the second law of thermodynamics? The second law of thermodynamics says that energy and matter tend to flow only from being in a concentrated spot to being one that is completely spread out. So energy likes to go from concentrated to spread out rather than spread out to concentrated. Why do we care about this in terms of chemistry? Because if we've got a system that's closed, energy will tend to move from an ordered state to a disordered state naturally. The opposite tends not to happen. So that leads us to the definition of entropy. So what is entropy? Entropy is a measure of how much chaos is present in a system at a particular temperature. Now, entropy, one of the things that drives your entropy value is the temperature of the system. Relies on temperature because if we think back to kinetic molecular theory, which we learned in September, an increase in the internal energy of particles, which means an increase in temperature, will increase the velocity at which those particles fly back and forth, and therefore create more collisions between particles, therefore creating more chaos. And what I have for you here is a quick little simulation to show this. All right, so here is a sample of a gas on a FET simulation. And what I'm going to do is I'm going to increase the temperature. So I increase the temperature, watch what's going on with each of these particles. It's going to heat it up quite a bit. And over time, you'll notice that the velocity of each one of those particles is going to increase. And I could keep going and going and going. And those particles just keep moving faster and faster and faster. And eventually it's going to blow the roof off of this particular container. Connection back to gas laws, as I increase temperature, I increase pressure. There goes the lid of the container. So notice that the particles became more chaotic with the more heat that I added to the system. This leads us to talk about reversible versus irreversible processes. So in order to do this, I inserted this video into what we call an ed puzzle. And I'm going to show you two videos. At the end of each of the videos, it's going to give you a prompt to answer a couple of questions. While you're watching these two videos, what I want you to think about is it easy to predict whether or not these videos are running in the forward direction or running in the reverse direction? Think about if it's easy or hard to figure out. Make a prediction which direction the video is running in, and then type your answers into the ed puzzle. All right, here's video number 1. This video comes from a site where they make videos for just cats. So technically, you could play this video for your cat for 12 minutes and entertain your cat. But think about, is it really easy to tell whether or not this video is running in the forward direction or it's running in the reverse direction? Ball goes left to right. Ball goes right to left. So this is video number 1. Last time the question, is it going in the forward direction, reverse direction, and was this easy to figure out? All right, here comes video number 2. Once again, same question. You can see the context clues at the top of the screen. Try to ignore those. Is it easy to tell whether this phenomenon is running in the forward direction, or is it running in the reverse direction? So let's talk about these videos. In the first video, what you will see is there was no overwhelming evidence that the video was running in the forward direction or running in the reverse direction. I don't know if it was running forward or reverse. I watched it time and time and time again. I can't tell. And the reason for this is a reversible process. When you roll a ball against a wall, that ball is going to bounce back in probably the same direction in which it came. And the amount of energy is not going to change all that considerably unless it keeps going over and over and over again. So we're going to say that that first video was a great example of what we call a reversible process. And you can't distinguish the forward direction of the process from the reverse direction of the process. So the ball rolling back and forth would be reversible. The path the ball traveled was very predictable and orderly. The amount of chaos before you rolled from left to right will be almost the same amount of chaos as you rolled the ball from right to left. Can't tell much difference in the amount of energy there. However, with the second video, you noticed that there was a lot of overwhelming evidence that this process was moving in reverse. And we know that because the system was going from a very chaotic pattern to a very orderly pattern, which is the opposite of what we know about the second law of thermodynamics. The second law of thermodynamics, things like to go to chaos. They don't like to go from chaos back to order. So, stuff being thrown down the stairs is an irreversible process. Is it possible for that stuff to be thrown back up the stairs and be put into the exact same order it was before? Statistically, yes, but probably not. So this particular system we can consider irreversible because it's going to such a state of chaos that it'd be hard to put back together again. So irreversible processes have high amounts of entropy. So what we mean by that is an irreversible process is going to be something that is statistically probable that could happen in reverse, but it's really, really, really highly unlikely. Just like throwing all of those items back up the stairs and having them land in the exact same location as where they started. Was it possible for Mr. Reverse, who is the director of all these videos, to throw those items back up the stairs and they'd land exactly in their starting locations? Yeah, possibly. Is it likely? Not really. Too many variables to consider there, and we don't go from a state of chaos to a state of order. However, is it possible for the cat ball to roll in the forward direction and roll pretty similar to in the reverse direction? Absolutely. It's absolutely likely. And we would probably have that occur if that ball was bouncing off a wall. And there are fewer variables to consider. Not much energy has transferred out into the system. So we can call that particular process reversible. So irreversible processes tend to be what we call spontaneous. So let's look at this waterfall here. Beautiful, serene waterfall. Spontaneous processes don't necessarily imply there's no outside forces necessary to begin the process, but spontaneous processes will continue on their own until a maximum amount of entropy is going to be reached. So if I'm looking at this waterfall, the water molecules are pushing other water molecules off the cliff. As those molecules will hit the pond down below, what will happen is those water molecules will disperse in a completely chaotic, random fashion. So you're going from a state of order where those particles were in a river, kind of packed together, into a state where they're more chaotic and all spread out. And it's happening spontaneously without outside intervention. So not all irreversible processes are spontaneous, but most are. So here's other examples of spontaneous processes. How about a ball rolling down a slope? You have to sit the ball at the top, but once you set it down, it will just roll down the slope on its own. Energy will transfer to the ramp, to the surroundings. It's going from a system of order where energy is compact with potential energy to a system that's more chaotic with kinetic energy. So it's going to be a spontaneous, irreversible process. Those balls are not going to roll themselves back up the ramp unless an outside force intervenes. Burning wood takes a catalyst of a spark to get wood to burn, but once it's burning, it's going to keep burning until it runs out of fuel. So burning wood is going to be a spontaneous process, but not only that, it's going to be irreversible because you can't take the carbon dioxide and the other carbon compounds that are created when you burn the wood, pack them back together and turn it back to wood again. So it's going to be irreversible and spontaneous. So in the video that you saw where I was reacting the zinc with the copper sulfate, that is again going to be a spontaneous process. All I had to do is add the zinc to the copper sulfate and mix it up a little bit, and then the reaction ran on its own. I went from a state of order where I had zinc in one bottle with very structured solid particles to a state of a more chaotic solution where copper particles were going all over the place. Energy was released. It's not going to be reversible. I can't make the copper into zinc again. So this is going to be irreversible and spontaneous. It'll just happen on its own. At this point, the Ed puzzle is going to ask you to think about 3 more examples of spontaneous processes or irreversible processes, which will also be spontaneous. And I also want you to note that all 3 of these examples are exothermic processes as well. The ball rolling down the ramp is actually exothermic because thermal energy is being transferred to the ramp via friction. It's fairly evident why burning wood is going to be an exothermic process because heat is going to be released out into the surroundings. And I told you in the video when you were watching the zinc plus the copper sulfate, the beaker got warm. Heat left the system of the copper sulfate and zinc and went out to the surroundings of the beaker, my hand, the classroom, so on and so forth. So I'd like you to think of 3 more irreversible spontaneous processes. And a good way to start to think about it is think of things that are tending to be exothermic. So here's another way to look at entropy. So in the previous examples, we were talking about energy spreading out. But how about particles spreading out? So here I'm introducing the variable for entropy, which is capital S. And entropy can also be defined as a way to describe the number of arrangements available to a system. So what do we mean by that? If there's more arrangements available to a particular system, the probability of finding the system in a particular arrangement decreases. So if I, for instance, decide to throw a bag of marbles out into my classroom, I go from a state of order to a state of chaos. And the marbles can go anywhere in my classroom. Therefore, I've increased the number of probable arrangements. Therefore, I've increased the entropy. The greater the amount of entropy, the greater the amount of chaos in that system. The greater the amount of chaos in that system, the greater the amount of energy in a system. And here's an analogy to that. Think of a bedroom with a lot of stuff, and I hope this is not how your bedroom looks during distance learning. So here's a bedroom with a lot of toys and junk all over the floor. If your room looks like this right now, stop what you're doing with chemistry and clean your room before you move forward. Make your parents happy. So think of a bedroom with lots of stuff. The more toys, the more stuff that's present, the more ways that they can be arranged. The more ways they can be arranged, the more chaos there is in the system. The more chaos there is in the system, the greater the nervous energy created for your family because they have to watch you throw stuff all over your room. So there's a good analogy for entropy. So it makes sense to say that if I go from a solid to a liquid to a gas, entropy actually begins to increase. So solids consist of very nice structured patterns where you have a sea of electrons floating in amongst the particles. This is an actual little video of an alloy being created at the particle level. But notice those blue particles are pretty much staying in one ordered pattern. Then I go to a liquid where the liquid particles don't have that structured ordered pattern and are kind of moving willy-nilly throughout the solution. And then if I change it into a gas, all those particles are going every which way whatsoever. So we can say that the entropy of a solid is going to be less than the entropy value for a liquid, which is going to be less than the entropy value for a gas. And the units to measure entropy, which were mentioned at the beginning of this video, are joules per Kelvin or joules per degree Celsius. Because once again, entropy is dependent on temperature. Hotter the temperature, the more chaotic the system's going to be. So solids have less entropy than liquids. They have less entropy than gases. So there's 3 ways to change the entropy in a system. First thing you can do is you can change the phase. So if I melt a solid into a gas, or a solid into a liquid, and then liquid into a gas, I'm definitely increasing the entropy. Stoichiometric changes. So this is the one that really has to do with chemistry. So if I perform a chemical reaction and at the end of the reaction, there's more moles of a substance present than what I started with, I've increased the number of possible arrangements of particles. So I go from a set amount of arrangements to more arrangements. Therefore, I'm going to increase the chaos. And if I increase the chaos, I'm going to increase the entropy. And you'll see an example of that in a moment. And then the last thing is to increase the volume if I'm talking about a gas. If I've got a gas in a container and then I increase the container, all of a sudden those particles have more places to go, so there's more arrangements possible. Therefore, I'm increasing the entropy. Think of a balloon. If I blow up a balloon, I'm not only just adding volume to that balloon, but I'm adding more gas particles, more collisions, more arrangements, more entropy. So here's some examples here. We've got two reactions going on here, and we're going to decide what the sign, SIGN, positive or negative, for each of the entropy for each one of these reactions will be. So I have nitrogen dioxide going to dinitrogen tetraoxide. And notice I've got 2 moles to start here, and I've got 1 mole to end with here. So I'm decreasing the number of moles. So if I'm decreasing the number of moles, I'm decreasing the number of particles, I'm decreasing the number of arrangements available in the system, so I'm decreasing, negative, the enthalpy. So this one is going to have a negative S value. Make that a little bit prettier here. And another thing that I can put is this little degree sign, because remember that degree sign will tell me the standard temp that I'm at standard temperature and pressure. And then let's look at this one here. I've got 2 moles to start with. I've got 2 moles at the end. So I have the same number of particles as I started with as what I ended up with. I have no information about change in temperature. I have no information about change in volume. So for this one, I'm going to say the S value is going to equal 0. And it's going to be equal 0 because I haven't increased the number of arrangements in that reaction, so I haven't increased the entropy. So the change in entropy, and I can call that change as well. I should put a change up here. The change in entropy of this value will be 0, and the one above here will have a negative change in entropy. Okay, so the final thing we're going to do here is we're going to find an equation to calculate the change in entropy in a system. This equation is going to look incredibly similar to how you find the change in enthalpy in a system and what we're going to be doing with Gibbs' law that's coming up next. So here is that equation. So the change in entropy in a system is going to be the sum of the entropy in the products minus the sum of the entropy in the reactants. And again, you're going to get those values directly from that data booklet. Side note, data booklets still in front of CHS, still in front of Griffin Middle School out on Steamboat. So notice that you've got the S here standing for entropy with a superscript of that little 0, reminding yourself that that is going to be calculated at standard temperature and pressure. So let's take a look at how this works with an example. Here is a paper 2 question from last year. It says, use the information below to calculate the entropy change of the formation of copper 1 oxide. So first thing we need, as usual, is a balanced chemical equation. So let's get that. So I've got my copper. Now copper is a solid, so it should have a low entropy, which I'm convinced of with a 33.3 joules per Kelvin. And that's incredibly low because joules is a very small unit of measure. And we're going to put that into some oxygen. And it's going to make some copper 1 oxide. And I have the formula here, but just to remind me why I've got a 2 here and a 1 by the oxygen, or copper and oxygen in a 2-to-1 ratio, the Roman numeral tells me that copper has a +1 charge and oxygen always has a -2. So you need 2 coppers for every 1 oxygen. And then I got to go back and balance. So I need a 2 here. Actually, I need 2 here to make 2 oxygens. And I need a 4 here to make 4 coppers. Now, another thing that I need to remember here is that entropy is a molar value. So I want this in terms of 1 mole. So I'm going to divide everything here in half to get 1 mole of my product. So my overall equation is now going to be 2 moles of copper will react with half a mole of oxygen to make 1 mole of copper 1 oxide. So now I'm ready to use my values to calculate the entropy change. So I got the entropy change is going to be the sum of the entropy of the products minus the sum of the entropy of the reactants. And that is going to turn into 101 minus, and I've got 2 times 33.3. Get this ugly mug out of the way. Plus half times 205. And I'm going to put this all into my calculator. And when I put this into my calculator, I get a change in entropy of negative 68.1 joules per Kelvin. Now, I have a decrease in entropy. That means that this particular reaction became more ordered. And it makes a lot of sense that this happened because I went from solid and a gas, that gas being of high entropy, to being just a solid. So I went from a more chaotic state to a less chaotic state. I went from a more entropic state to a less entropic state. So I should have a negative entropy value here, which is a double check when you write your balance equations and you look at your state of matter. You can also tell that I go from 2.5 moles to 1 mole. So I should have a decrease in entropy here as well. So that's it. That's how we do calculations to find the change in entropy in a system. So this video covered for you what is the second law of thermodynamics, what's entropy. Hopefully you can see how entropy changes over time in spontaneous processes and irreversible processes. And then we finally calculated entropy using values from the data booklet. Hope this all made sense. Have a great day.